As we've said before in the channel, temperature is one of the most important parameters in electronics. But now we'll talk about temperature in a different manner. Now we will discuss how to measure it. There's many ways we can measure temperature, but today we will check in a specific one of the cheapest and most popular temperature sensors in the market, the LM35. Now, why is this sensor so popular? Because of a few reasons. First, because the sensor is quite simple. It only has 3 pins: VCC, output and ground. Also, the output is linear, so measuring it, either through an analog or digital method, is quite simple. The accuracy is also nice, being of a value of 0.5 degrees Celsius. And at last, there's a price, which is around $2 to $4 per unit in low volume. So, how does this sensor work? The structure is quite simple. We have a current generator being made out of 2 transistors and an op-amp in differential mode. Then we have the semiconductor element that varies its resistance in function to the temperature. And at last we have the buffer, being made out of an op-amp and a voltage divider. This is how the output is stable at 10 mV per degree Celsius. Well, now that we comprehend the functionality of the sensor, let's analyze the datasheet of the sensor to know its operating values. First, we have the maximum operating voltage, being 30 volts. If we exceed this value, the sensor will get damaged. Then we have the maximum output current, being 10 milliamps. We must remember that this sensor cannot handle big loads by itself, so the output signal must be buffered before using it to control something else. And at last, we have the maximum temperature, being 150 degrees Celsius. Due to this limit, this sensor might not be suitable for some applications, obviously being high temperature operations, but it is very useful for ambient readings. Also, the maximum temperature varies in function of the model, specified in the table, so first be sure that you know the specific model of the sensor to know its limits. In terms of accuracy, we can see that the manufacturer specifies a value of 0.5 degrees Celsius of variation at 25 degrees Celsius ambient, but the maximum variation manifests with the ambient temperature being over 100 degrees Celsius. Here it's when the accuracy changes to plus minus 1 degree Celsius. And at last we have the quiescent current. This value will change depending on the ambient temperature and operating voltage, but we can expect values between 90 and 120 microamps. This is a very important value to take in mind if we operate with batteries. Then we have the values that specify the sensor performance in 4 different cases. First case being 25 degrees Celsius with an accuracy of plus minus 0.2 degrees Celsius. Second case being minus 10 degrees Celsius with an accuracy of plus minus 3 degrees Celsius. Third case being maximum temperature with a value of plus minus 0.4 degrees Celsius. And last case being minimum temperature with a value of plus minus 0.4 degrees Celsius. Then we have the sensor gain, which means the output value increment in function of the temperature. In this case, it changes between 9.9 mV per degree Celsius to 10 mV per degree Celsius. Now that we have checked the general data of the sensor, it's time to probe its values in the lab. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In PrismaSem Network, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. So here we have the first test, and it involves the LM35 against a thermocouple thermometer. We have the multimeter that shows the LM35 output, so we are at around 22 degrees Celsius. Remember that we have 10 millivolts per degree Celsius. And we have a laser thermometer which also indicates 22.3 degrees Celsius, so we can compare the values between the three of them. So the offset between both of them is not quite big, to be honest. So here we can test the difference when I apply my body heat to the sensor, in this case the thermocouple. It rises up to 33 degrees Celsius. Now we test with our LM35. Let's see how much it rises up. Now we have to understand that the epoxy body of the LM35 is not the best thermal conductor there is. So obviously applying heat from my hand to the sensor, it's not going to be the optimal application, to be honest, because there's going to be some losses in dissipation and such. So in this case, we are barely rising up to 30 degrees Celsius. So that's as much as we can expect. But if the sensor was a metal body variant, then we will see another story. But in this case, that's as much as we can see. So in this second test, we're going to measure the maximum voltage that we can fit into the sensor. Here we have 33 volts, and we're going to rise it up to 60 volts to see how long does it take to damage the sensor. At the left, we can see the multimeter with the sensor output. On the right, we have the supply voltage. And we are already at 42 volts and rising up. We have to remember that the datasheet mentioned that the maximum voltage recommended by the manufacturer was 30 volts. And here we are almost at 20 volts over the recommended maximum value, and it's still operating. So it's quite a strong semiconductor we have here. Also noting that we have virtually no load into the sensor. So we are at 50 volts and the sensor is still operating. "55 volts and the sensor refuses to die," so quite impressive. Now, why this happens, there's multiple number of reasons. First, the unique variants of the semiconductor and other factors such as the ambient temperature and the fact that we have no load into the sensor, such and such. But just because this one survives the twice the voltage supply doesn't mean that we should implement the sensor in such operating characteristics. So we need to respect the values of the datasheet, even though in this case the temperature is quite comfortable, operating way above the maximum values. So now we have the quiescent current test. We are operating at 5 volts and we have 54 microamps. Here we have on the right the value of the quiescent current and on the left the output voltage. So this is our value, which is quite lower than the specified in the datasheet, which was 90 microamps. Now we're going to modify the voltage supply up to 30 volts and see the change. Remember that the quiescent current depends on the voltage supply and on the temperature. So now we have 30 volts and we have virtually the same value. So voltage seems not to be the most important factor in the quiescent current value. And if I apply my body heat, we can see that the quiescent current starts to rise up, which means that temperature is going to be the main factor in this value. So the higher the temperature, the higher the quiescent current value. So now let's test it up with a lighter to rise up the temperature quite quickly. We can see on the left the temperature output, and we can see the quiescent current rises up according to the temperature. We're going to try to rise it up to the highest value possible to see what is the highest quiescent current that we can output with this sensor. So we are almost at 70 degrees Celsius and we have over 70, now we're at 80 microamps, 90 microamps at 100 degrees Celsius, and we are going up. So let's apply again. 120, 130 degrees Celsius, and we have over 100 microamps. So this is quite a high temperature to operate in. The value of the quiescent current is not so high. So we expected a higher value from the datasheet, but we got quite a good deal in this case. So now let's let it cool it off, and we can see the quiescent current starts to drop its value to what it was before. Now we are at 48 degrees Celsius and we have 64 microamps and going down. So is this a good value enough for a battery operated circuit? It depends on the battery, it depends on the expected longevity of the charge. So it might be, it might not be. Obviously there's other sensors that require way less current to operate. So you should choose from one of them, but this one kind of operates within a respectable value. Well, in this first part, we simply have seen the theoretical part of the sensor. In the second part, we'll see the practical functionality, and we will learn how to measure the values of the sensor with a microcontroller.